Today we're going to be talking about section 5.2, the characteristic equation. In our last video, we talked about eigenvectors and eigenvalues, and we talked about if given a vector, how do you see that it's an eigenvector or not? And given a number, how do you tell if it's an eigenvalue or not? Today, we're going to be focusing on if you're not given a number, but you still want to figure out what all of the eigenvalues of A are, how do you find the eigenvalues? So before we were given a specific number and we wanted to check if it was an eigenvalue, now we're going to just find the eigenvalues from scratch. So let's recall something that we saw in our last video, which is lambda is an eigenvalue of A if and only if we do this special factored form A minus lambda I times X equals 0. If that has a non-trivial solution, then lambda is an eigenvalue of A. So let's go ahead and look at a specific eigenvalue. So if 0 is an eigenvalue of A, then the A minus lambda I, that's going to collapse down to A minus 0 times I, which is just A. So this becomes A x equals 0 has a non-trivial solution. So let's think about what this actually means. If Ax equals 0 has a non-trivial solution, then if we look at our invertible matrix theorem, which I've written a couple of pieces down below, that means part D is false. And if one thing in all of this list is false, then all of the things are false. So in particular, if 0 is an eigenvalue of A, then part D is false of this theorem, so A is not invertible. So this means we can actually add a couple of extra things onto our theorem. So again, I've reproduced a couple of things here. The last time we left off with this was part R. So we were talking about dimensions of null spaces and column spaces. Now we'll add on a part S. So part S is here, if 0 is an eigenvalue means that A is not invertible, then if A is invertible, then 0 should not be an eigenvalue. Another one that I'm going to put on here we already talked about, but we hadn't actually written it down in the whole list, which was A is invertible if and only if the determinant of A is not 0. So these are our two new pieces to the invertible matrix theorem. Okay. So we just saw a specific example of how to tell whether 0 is an eigenvalue or not. So if A is invertible, then 0 is not an eigenvalue. How do we tell what the eigenvalues are in general? Well, it's actually very similar. We're going to use these pieces of the invertible matrix theorem that we just found to figure it out. So if we want to find eigenvalues of A, what do we need to find? We need to find for what values of lambda does A minus lambda I x equals 0 have a non-trivial solution? Well, if this has a non-trivial solution, that means part D of the invertible matrix theorem is false. So that means that this matrix is not invertible. In particular, this matrix, in this case that we're talking about, is A minus lambda I. So this is not invertible. So if this is not invertible, then that means every single thing in that list is false, including the fact that the determinant is non-zero. So if A minus lambda I is not invertible, that means that the determinant of A minus lambda I should equal 0. So what does this mean? This means that if we want to find our eigenvalues, we need to find for what values of lambda does the determinant of A minus lambda I equal 0. This is how we're going to find our eigenvalues. This is, in fact, such a useful way of finding eigenvalues that it has a special name. It's called the characteristic polynomial. So the characteristic polynomial of A is this determinant of A minus lambda I. And the characteristic equation of A is the determinant of A minus lambda I equals to 0. That's the characteristic equation. So again, lambda is an eigenvalue of A if and only if it satisfies the characteristic equation. So if and only if determinant of A minus lambda I equals to 0. So To recap all of this, how do we find the eigenvalues of A? First, we make this matrix A minus lambda I, and then we use that to find the determinant. And this is, again, the characteristic polynomial. So we want to find the determinant of A minus lambda I. We go ahead and set that determinant equal to 0 for the characteristic equation, and then we factor that to solve for lambda. So let's take a look at what this looks like in action. So this is problem 2 in your textbook, section 5.2. And problem 2 is asking us to find the characteristic polynomial and eigenvalues for this matrix. So in particular, let's start off with making our A minus lambda I. So again, we don't know what lambda is yet, so we're just going to use lambda as a placeholder. That's what we're trying to solve for. And so let's go ahead and find this. We have 5 minus lambda, and then 3 minus 0, which is just 3, 3 minus 0, which is just 3, and 5 minus lambda again. So then the next thing we want to do is we want to find the characteristic polynomial. So the characteristic polynomial is just the determinant of that thing we just found. So the determinant of 5 minus lambda, 3, 3, 5 minus lambda. So we find the determinant by taking the product of the on-diagonal entries and subtracting off the product of the off-diagonal entries. And let's go ahead and simplify that down. So this would give us 25 minus 10 lambda plus lambda squared minus 9. So this is lambda squared minus 10 lambda plus 25 minus 9, which is 16. Okay, so now if we want to actually find so this is the characteristic polynomial. So we've done the first part of the problem. Now if we want to find the eigenvalues are the lambdas that satisfy our characteristic equation. So in particular, we're going to go ahead and take that characteristic polynomial, the determinant that we just found, and we're going to set it equal to 0 and try to solve for lambda. Now in this case, this factors pretty nicely, right? So this is lambda minus 8 times lambda minus 2 equals 0. So if we want to solve for lambda, we get lambda equals 2 and lambda equals 8. So these are our two eigenvalues. Of course, if it didn't factor so nicely, or if we didn't see that, we could use the quadratic formula. So let's maybe go ahead and try that out. So lambda would equal the opposite of b. So here b is our minus 10. So we get 10 plus or minus the square root of 10 squared. 10 squared, there we go, minus 4 times 1 times 16, all over 2. And we can simplify that down a little bit more. So this is 10 plus or minus the square root of 36 over 2. And of course, the square root of 36 is 6. So this would give us that lambda equals either 10 plus 6 over 2, which would give us our 8, or it would equal to 10 minus 6 over 2, which would give us our 2. So either way that you want to do this is fine, but now we found our lambda, so those are our eigenvalues. Let's take a look at another example. So this is problem 8 in section 5.2, and it's asking for the exact same thing. It wants you to find the characteristic polynomial, and it wants you to find the eigenvalues for this matrix. So let's start by finding our A minus lambda I. So again, we're just subtracting lambda off of the main diagonal, and then the off-diagonal entries stay exactly the same. So we'll then find our characteristic polynomial, and our characteristic polynomial is just the determinant of that thing. So we find the determinant in the same way as we always find the determinant of a 2 by 2, which is taking the product of the on-diagonal entries, so in this case 7 minus lambda times 3 minus lambda, and subtracting off the product of the off-diagonal entries, which is minus 4. So this would be 21 minus 7 lambda minus 3 lambda, so that would give us minus 10 lambda plus lambda squared plus 4. So if we simplified that down a little bit more, this gives us lambda squared minus 10 lambda plus 25. So now this is our characteristic polynomial, and to find our eigenvalues, we go ahead and set that thing equal to 0. So we've got lambda squared minus 10 lambda plus 25 equals 0, and this is just lambda minus 5 squared. So we only have one eigenvalue in this case. Our one eigenvalue is lambda equals to 5. But this eigenvalue, because of the squared, it shows up twice. So we say that this has a multiplicity of 2. And a multiplicity just is the number of times that that eigenvalue shows up as a factor in our characteristic equation. So because this is squared, we say this has a multiplicity of 2. All right. Let's try one slightly bigger example. So we were doing 2 by 2s before. Let's actually do a 3 by 3. So we want to find the characteristic polynomial for this 3 by 3. It doesn't ask us for the eigenvalues because often these are really hard to factor because now instead of quadratic equations, they are cubed. So this is just asking us for the characteristic polynomial and not the eigenvalues. If you wanted to actually find the eigenvalues, you would ask a computer to factor that for you. So our characteristic polynomial, again, is going to be the determinant of this a minus lambda I. And in this case, that would be the determinant of, again, we're going to take every on-diagonal entry and subtract off lambda. And then the off-diagonal entries stay exactly the same. This is 4 minus lambda, 1, 0, 0, 2 minus lambda. So this is our a minus lambda I. And we want to find the determinant of that. And so because the third row has all zeros, I'm going to go ahead and expand along that third row. If we look at our checkerboard pattern, this is a plus minus plus along the first row. So if we go down this column, we've got a plus minus plus, so that 2 minus lambda is a plus. So to find the determinant, we do 2 minus lambda times the determinant of the 2 by 2 matrix that's left over when we remove the third row and third column. So that's minus 1 minus lambda, 0, minus 3, 4 minus lambda. So this would be 2 minus lambda times minus 1 minus lambda times 4 minus lambda. I guess minus 0 times negative 3, which is just minus 0. So here our characteristic equation, if we wanted to find that, we would go ahead and multiply that all out. Instead, what I'm going to do is leave it factored. In your homework, you can multiply it all out. The reason why I'm leaving this factored is because I mentioned at the beginning of doing this problem that often 3 by 3s, you're not going to find the eigenvalues by hand because it's hard to factor the characteristic polynomial, but here it's pre-factored for us. So here we can read our eigenvalues right off of that. So we have lambda equals 2 would be an eigenvalue, lambda equals negative 1 would be an eigenvalue, and lambda equals 4 would be an eigenvalue. So to recap, today we talked about the characteristic equation and the characteristic polynomial. The characteristic polynomial is just the determinant of a minus lambda I, and the characteristic equation is setting that equal to 0. And we use these to help us find eigenvalues for a matrix. And we find the eigenvalues by just solving what lambdas would satisfy the characteristic equation.